Welcome back to Mike and Chris Do Physics. I'm Mike, and today we're going to review vectors. So you should be in the physics mechanics playlist right now, and we have to start with the basics of a vector because you're going to see vectors all the time in physics. And remember that a vector is just a very special object, right? But in math, we like to do math with objects, right? And in physics, it turns out doing math with objects is really, really useful in describing the real world. So up until now, you've dealt with numbers that are scalars, right? Scalar is just a very fancy word for a number that you've known and used for all of your short math career. But a vector has a number, two numbers associated with it. One is the length of the vector, which could represent anything that a scalar could represent. It could be how far you walked, it could be the speed that you're going, any number of things. And then there's another number that comes with it, which is direction. Because me walking that way 10 meters is not the same as me walking that way 10 meters. So we have a single object called a vector, and we have two numbers that describe what that vector is doing. So why do I care? Because in physics, direction matters. If one person is going this way at some speed and another is going that way at some speed, then clearly two different actions are occurring, and we want to be able to describe both. And we wanted to describe both in relation to each other, which is going to get a little tricky, but that's a lesson for the future. So for today, what we're going to do is just focus on vectors. This should be review. If not, then you may want to go find a longer lesson on vectors. What do you need to know? If you already know trig, you're set. I will review that a little bit as well. And I guess you just need to be pumped about learning vectors. I don't know. That's all you need, right? You just need to be excited, and let's get after it. So here we have a vector. That is just an arrow here, basically. And we've got two components of this arrow. The first is its length, okay? The length of that vector is its magnitude. So we'll say this is the magnitude. And remember that the length of a vector can just be a scalar, right? It's just how far I've gone, that's just a number. It's how fast I'm going, that's just a number. Okay, so whatever this vector describes, the number that describes it is the classic scalar. And you can just think of this as a number, although this isn't specific enough, right? So we tend to use magnitude. Magnitude implies that it's a vector, but we're only talking about the scalar aspect of that vector, i.e. the length. So I don't really like to use number. Maybe another way to think about it is length. Okay. Now the next question is, what direction is it headed? Is it headed? Let's try that again. And you say, Mike, it's headed this way. I can see, like the arrow shows me exactly where it's headed. Okay, but in relation to what? And the answer to that is we need an axis or a coordinate system. Okay, so I'm going to draw a little coordinate system up here. The easiest coordinate system for us to draw is the one, that was a terrible Y, let's try that again, is the one that we're used to, the y-x axis. Okay, so if we kind of set our coordinate system up like this, then maybe it's obvious, and I'm going to scoot this away here a little bit so I've got enough room, that this angle right here, okay, if this is the x-axis and this is the y-axis, okay, then that angle right there, theta, that is one way in which we can describe the direction of this thing. What do I mean by one way? There's going to be more than one way, okay, which is going to be a little bit frustrating. But I could describe this as, I don't know, that looks like maybe not quite 45 degrees. Maybe we'll call it 35 degrees, right? We could say that's 35 degrees. In this case, what? If we wanted to go with cardinal directions, it would be north of east. Or we could just leave it as 35 degrees and understand that that's always the angle between the vector and the x-axis, right? Going around counterclockwise, right? We always measure angles like that. So there's a couple other different ways that we can measure this too. So let me show you what I mean by that. So let's I can steal arrows with this thing so I don't have to constantly redraw them. Okay, let's suppose that this vector had a length of 10 and the 10 was 10 steps. So you took 10 steps in this direction. Okay, well there's another way that you could have gotten here, and the other way you could have gotten here is by going a certain number of steps. You know what? I'm going to choose a different number of steps, and you're going to see why in just a second. Okay, we'll call that 5 steps, right? I could have gone 4 steps to the right And then I could have gotten 3 steps up. Maybe now you see why I changed that to 5, because I have a 3, 4, 5 right triangle here. So this is still the angle. That angle, well, it's no longer 35 degrees. We'd have to do a little trig to figure out that angle. But I could still describe the direction of this arrow as an angle. I could also describe this arrow, kind of the point in space that this arrow points to, by saying, well, I'll just go 4 in the x direction, 3 in the y direction. Okay? So this would be the x component of that vector. X component. This is physics, not spelling. Don't judge me. Okay? And this would be the y component of that vector. Cool. So we have a lot of different ways to kind of physically describe these vectors, and I will go through a little bit of math. But first, we need some symbols, right? Every time we have something in the real world, we want to give it a letter or give it a symbol so that we understand mathematically what we mean when we start playing around with these objects. If you go to the store and buy a CD, you could buy X CDs, and X just stands for the number of the CDs. So we need a symbol that stands for a vector, and we can use letters, except we want to differentiate vectors and scalars, right? So classic scalars that you are used to might just be y, it could be x. I mean, it could be anything that you want, right? But we need a new symbol. So we are going to write a little arrow on top to indicate that y and x and any other letter that we use is a vector, all right? And so this little arrow just tells you there are 2 pieces of information that have to come with this y vector, at least 2. Right? So our vectors can have, we can be in 3 dimensions, and then we start running into other issues, okay? But for right now, we'll stick with 2 dimensions. And so that's what I'm going to need in order to actually describe everything that's going on with this. I need 2 numbers, not 1. Okay, cool. And now you might say, well, hold on, Mike. What if I only care about the magnitude of this vector? Can I just write y? And the answer is yes, you can. And this confuses students a lot. So let's go down here, right? This vector is, the length of this vector rather is 5. And there's a couple of different ways we can do this, all right? So I'm not gonna write out what the vector part of it looks like, but you could say y is 5. Now, with no context at all, you might say, is that just a scalar, or is that the magnitude of some vector? And the truth is, at the moment, you don't really know. So you've got to have a little bit more information. And the way that we do this, and this is kind of clunky, the way that I can indicate that this is actually the magnitude of a vector is I'll write the vector, but then I'll put these 2 double bars on both sides, okay? This, let's write this out, this means magnitude. Magnitude of a vector. Okay, and the magnitude of this particular vector is 5. So the one on the left, we are lazy, and we sometimes just write y is 5 because it's a lot faster than all these other extra symbols. But if we really want to be super clear, or the context isn't obvious, if I write it like this, this definitely indicates that we have the magnitude of some vector y. Okay, the last part then is, well, how do I indicate the direction? And the truth is, we typically don't like to write the angle if we can avoid it. It's kind of an awkward way to write it. We typically like to write it in terms of the x and y components. And I'll show you why. It's a little bit easier to do it this way. Okay, so for example, let's say that I don't want to use y because we've got x and y here. So I'm just going to use r. Well, let's use r. Little r is my position vector. You'll see this in physics a lot. So I'm going to make this a little vector. Okay, and r, this r vector is just pointing, is this vector right here, okay? And, well, what is it doing? It's going 5 steps, but it's going 5 steps in some weird direction. And we like to write things in terms of x's and y's. It's just, I don't know, it's easier. We like it. And there are a few different formats that we can write it in, which is annoying, but it's useful in different contexts. And so I'm going to show you some of the different formats. One of the ways that we can do this is we can say this is 4x hat. This little caret's called a hat. I'll tell you what that is in just a second. Plus 3y hat. Okay, what in the world is going on here? This notation is ridiculous. Well, the problem is that I need a little vector that describes the direction that x is in, right? This is a vector. I can't just add 2 numbers to make a vector. I have to add 2 vectors to make a vector. And so what we say is, if I'm looking on the on the x direction here, let me use a different color, okay, that there is a little vector going this way of length 1, and we call that little vector going that way the x hat vector, okay? So the magnitude of the x hat vector is just 1. Why do we use a hat instead of a vector? Because it's a very special vector. It has length 1. Why is that important? Because now I can multiply by 4. 4 times 1 is just 4. I never change the length of something when I multiply it by a scalar. Okay. Likewise, and maybe we'll use blue. I don't know. Blue sometimes doesn't show up. We'll use green. Okay. I'll have a little vector of length 1. What do you think that one's called? Can you guess? It's called y hat. Hopefully you got that right. And the magnitude of y hat is also 1. So I just have these little vectors of length 1 with that point in the x and y direction. Okay, and then I can multiply those by some number. So 4 times x hat is a vector in the x direction of length 4, plus a vector in the y direction of length 3. And sure enough, that mathematically describes exactly what I've done here. I move 4 in the x, I move 3 in the y, and there we go. I'm at the point that my r vector describes. Now, we can also write it another way. This is really going to piss you off if you've never seen it before. Sometimes we don't like x hat and y hat because we're going to have variables later. Like later at some point, I might have 4x x hat. And we just, I don't know, we just don't like seeing x's and y's doubled up like that. I don't know why. Okay. Some other formats you'll see. Sometimes instead of x, you'll see I hat. And instead of y, you'll see j hat. Okay? It's not any different. They are both vectors of length 1. The I hat vector is a vector of length 1 in the x direction. J hat, vector of length 1 in the y hat direction. And so I could also alternatively write this way, 4 I hat plus 3 j hat. Now, if you've never seen that before, that looks silly and funny. But for those of us that have been doing vectors for a long time, this is actually, I think, the most common way to write it. I haven't seen any physics classes that use x hat and y hat. Sometimes you'll see that in math books. Okay, so this is kind of the way that's kind of the way that I would write it. All right. How else could you write this vector? Sometimes we leave off the little letters completely. All right, and we use these little brackets, these little angled brackets, and we just write 4, 3. That is also a totally legitimate way to write a vector. You will definitely see that in math classes. And this says the same information. The first number is the x direction, it's implied, and the second number is the y direction. Okay? And of course, you could always just write that this vector is some number of degrees. You could write it as like a sentence. It's just not nearly as neat. So, and I'll review the trig here in just a second, but this angle happens to be, I think it's like 36. Hold on, I did this earlier. 36.87. So this is 36.87 degrees. Okay, you could, if you wanted, you could write it this way. You could say, r hat is a, vector of length 5. So you could say like, 5 at 36.87 degrees, maybe like north of east. Okay, this is not a mathematical way to write this. We don't like this, right? This is not very fun. But sometimes kind of in a basic physics class, you might start with this so that you get some practice with that ugly pre-calculus stuff and make sure you know where these things are pointing. For those of you that are super into polar coordinates, yes, you could describe this as just a distance and an angle, right? So if you've done polar coordinates before, I won't assume that you have, but for those of you that have, then yes, you can just describe this with two numbers, 5, 36.87 degrees, or if you wanted to convert that to radians, you could do that too. That is also a way to represent this, but you would need to indicate that you were in polar coordinates. And if that didn't make any sense, don't sweat it. Okay, next we need to add and multiply vectors. So here I have two vectors, vector A and vector B. You can see they both have different magnitudes. They both are at different angles to the x-axis, so they're in different directions, and I want to add them together. Now, I think the easiest way to think about adding vectors together is, well, if I take, 10 steps in this direction, and then I take another, we'll call this 3 steps in that direction, I might end up over here somewhere, okay? And so we want to just stack these vectors on top of each other. And so visually the way we do this is I'm just going to grab, let me grab the label too. So let me grab this vector. Okay, and I will just stack on this other vector. Now we need to be a little bit careful here. We always want to go tip to tail, right? What do I mean by that? The tip of the A vector here adds to the tail of the B vector here, right? And we'll move these labels out of the way. And the resultant vector, I guess maybe we'll do that in green, looks like this. Okay, so that's how we do it visually. And for most folks, I think this makes a lot of sense. The question is, how do we do it mathematically? Okay, and I stole my B vector here. Oh no, I didn't want to move it. I just wanted to copy it. There we go. Oh, what a mess. All right. This is a great tablet. This is the remarkable tablet, by the way. If anybody's interested, I get that question sometimes. It's a great tablet. Okay, what I want to do, though, is I want to say, well, look, if I can just add A and B tip to tail like this, well, then surely I can add the x direction of A and the x direction of B. And I can add the y direction of A to the y direction of B, right? I can always add things in the same direction to each other. So let's do that. And if I want to do that mathematically, yeah, maybe we'll do it visually first, right? So this would be the same as if I had done this. Let me steal these two arrows. We're going to copy them. Okay, I'm just going to show you that we should get visually the same thing here. Actually, let me park this guy here, okay, and park this guy here. And so what have I done? I've just added the A and the B vectors, but only their x components together. And then let's go ahead and steal this guy. Okay, and there's the y component of A, and we'll add that to the y component of B. Okay, oh, we don't need that little guy. Perfect. Okay, and you can see that gives roughly the same answer. It should give the same answer. Okay, if I had done this exactly right. And you can see there's some spaces here. It's not quite perfect, but you get the idea. Okay, so that is the easy kind of mathematic way to do this. Now, if I want to do math with these components, I need labels for the components. And so it's very simple. We just take this vector A and we write x down here. That indicates I'm talking about only the x component of that vector. Now, you'll notice I have stopped writing the arrow over top. It doesn't mean it's not a vector anymore, and I know this frustrates some folks, but when I write this little subscript x down here on the bottom right, it indicates it's still a vector, but I'm just talking about the x component of a vector. So you already know what direction it's in. It's in the x direction. Likewise, this would be b sub x, this would be a sub y, and this would be b sub y. Okay, so knowing that now, right, if we go down here, and this is a sub y and b sub y, then what is the total length of this vector, right? Which is the y component of the new green vector. Okay, it's just, so maybe I'll write this new vector as c. Okay, so this is the c vector. So then the y component of the c vector, and we'll try to keep the colors consistent here, would be, let's see, a sub y plus b sub y, right? So we'll go with red. It's the y component of A plus the y component of B. And that's visually we can see that. Mathematically we can see that. That's great. Now we'll go to the x component of this new C vector. All the x's I've written in blue. And so we have the x component of A plus the x component of B. And now we're done. Like, we have our vector C. If I want to write it in terms of these other two vectors that I've added up, what did I do? I just got the x components in the x direction and the y components of the other vectors in the y direction. So I could write this a number of ways. Maybe we'll just write it two ways. So I could write ax plus bx, right? All that's in the I hat direction, plus ay plus by in the j hat direction. Or if you like this caret method, this little bracket method, this is ax plus, whoops, I'm back up there. It's not a comma, should be a plus. Okay, plus bx, and let's see, ay plus by. Okay, those would be the two components there. And that's how we add vectors together. All right. What about subtraction, you say? We need to understand multiplication, so let's go multiply a vector first, and then the subtraction rather should be obvious. So here we're going to multiply, and we're going to multiply by a scalar. Well, what does it mean Could we multiply two vectors together? And the answer to that is yes, but it's complicated. And we're not going to cover it today. And we'll cover it in the actual course of the physics instruction when we need it. But multiplying by a scalar is really easy, right? So if I have some vector A and I want to know, what 2 times A is, well, then I'll just do 2. And the thing here is I'm multiplying by a scalar. Remember, a scalar doesn't have any direction involved, so I'm just doubling the magnitude of my original vector. Okay, that's no different than adding 2 vectors right on top of each other. So there is 2A, right? Whoops, let's draw this right here. That right there is 2A, okay? So multiplying 2 vectors together is the same as just adding them together, or not 2 vectors together. Multiplying by a scalar is the same as adding them together a certain number of times. So that's kind of the classic multiplication that you're familiar with. But what happens if I do this? What happens if I want -1 times A? What does the negative do? Okay, in physics, in all of physics, our positives and negatives are always going to be directions. Negative means go the opposite direction, right? So if I'm looking at my XY coordinate system, okay, here's my Y, here's my X, and remember we said that, I hat goes like this. That's my I hat direction, and my J hat is my Y direction of length 1. Okay, what if I want to go to the left? What if I want to go this way? Okay, well, if I go this way, we'll just call that negative I hat. And what if I want to go down? You guessed it, negative J hat. So negatives just mean flip direction. Go the other way. So let's take this A vector again. All right. Give it its little vector head. And if I want negative A vector, I will just flip this guy around. And this is really cool. You ready? I think it should snap. Oh, it didn't snap. Normally it snaps to like 180 degrees. But that looks pretty parallel. We'll call that a win. This would be negative A hat. Okay? All it does is flip that vector around. And that's important because now we know how to subtract vectors. So let's go back. Let's say I have, here's my A vector. That's like roughly what I had in the last example. And then I had B, looked like that. A little steeper, a little shorter. Okay? And the question is, what is A vector minus B vector? Well, let's write it like this. Let's say this is A plus a -1 times B. It just means flip B around and then add them. Okay? So let's do that. Let's grab our arrow here. And, maybe I just... Oh, there we go. That's how we get it. Perfect. Okay, so this guy right here is now negative B, right? And now I just add these two together. And so, well, we'll just grab it here, right? There we go. There's A plus a negative B. Okay, so this vector right here is A minus B. And I've just added a negative version of B. Okay, vectors, let's just do a couple of really boring rules just so you have a copy of the rules, and then we'll call it a day. Just kidding, I lied. We need to do a very quick trig review. All right, I'm not going to go through a lot of detail on this because you should have had trig before. And again, if you need to review it, please review it. But how do we actually get the components from the original vector, right? How do I get these x components, y components, right? So if I have, let's say I have 5 and I have 36.87 degrees or whatever it is, right? It, generally speaking, we'll say this is a vector, right? And, or I guess this, well, up here is just the magnitude. And then here is theta, right? So this is, I don't know why I wrote a comma. This should be theta. Okay, how do I get the actual components? How do I get the x component and the y component of A? Very basic trig review, right? How do I get this angle here, or the ratio rather, around this angle from the side and the hypotenuse? That is the cosine, right? That would be the cosine of this guy. So I'll do it the long way first. So we'll say cosine of theta is adjacent over hypotenuse. So that would be the x component over the magnitude. Okay, and then I can, well, what can I do here? I can multiply the magnitude over, and I can say the x component is equal to the magnitude of A times cosine of theta. Okay, so this is how we're going to get our x component, right? It's just the magnitude times cosine of theta. That should look really familiar. Of course, you can do the same thing with sine, okay? And so that we'll get the y component ends up being the magnitude times sine of theta. And you should be really comfortable with this. If you're not comfortable with this, I just recommend that you go back and do some basic trig review. I don't know why my square didn't snap there. Come on, square, you can do it. All right. And of course, there's a couple other relationships. If you need to solve for the angle, you can do the tangent of theta is what? The y over the x, right? So it's the y component over the x component. And of course, you can always arctan both sides, right? Okay, fine. I guess I'll just write it. Theta is sometimes called the inverse tangent or the arctan of the y component over the x component of that vector. So all the trig, that's why we study trig. Okay, well, there's a couple of reasons why we study trig, but this is the big one, is that vectors, we're always making triangles with these vectors, with our x components and our y components, and we need to have trig to describe all of those relationships. And then, of course, maybe the most classic one, we know that we can just do Pythagorean theorem here as well. So a sub x squared plus a sub y squared is equal to the magnitude of a squared. And you can always find that as well. Okay, now on to our boring rules and properties, and we'll call it a day. All right, we got to know the properties of vectors, and these should be reasonably obvious, but so I'm not going to prove them, but we'll just make sure we understand how these things work and make sure that many of the same rules apply with vector math as with other kinds of math. Not with multiplying two vectors. Again, we didn't cover that today. We'll cover that later. Okay, number one is the distributive law. I can take any scalar, I guess we'll call it S, and multiply it by these two vectors, a plus b, and it distributes just like it always does, right? So you can either add these vectors first and then multiply the scalar, or you can do S, the scalar times this vector a, and then the scalar times this vector b, and then add the resultant vector there. You're going to get the same answer either way. So this is the distributive law, and we'll call it form 1 because there's another way we can distribute. What if I have a vector times two scalars? So we'll say vector a times scalar plus, I guess I need another letter. We'll just go with the next letter, t. Okay. It also distributes. No big deal. You can just add these together and then multiply by the resultant scalar, or you can separate it out if you like, and you can do s times a vector plus t times a vector, and that is the distributive law, and I guess we'll call that form 2. All good. You can distribute all day long. Rule number 3, this is like the annoying math stuff that we just like to cover to make sure we know all the rules. If you multiply a vector times 1, you just get that vector back, right? So multiplying by 1 doesn't do anything. You're familiar with that, but with scalar multiplication. Why do I write that? Because -1 does something a little bit different, right? I get a negative version of the vector, okay? And you go, this looks the same. Good. If you think it looks the same, it's because it is the same. But we still need to show that there's a negative sign here, and that all the individual components have flipped. The x component's going the other way, the y component's going the other way. Everything turns around. Okay, and then finally, this would be the easiest one. 0 times any vector is the 0 vector. Okay, what? What? Why does it 0 vector? It's not pointing anywhere. I know, don't get mad, but it's still a vector. I can't, in math, I can't multiply a scalar and a vector and then not get a vector. That, like, it breaks the rules. I don't know. People don't like it. Okay. Also, you will see, I don't know if I can do this well on my tablet, but we'll try. Let's go with a marker. Sometimes the 0 vector is written, well, that's the wrong color, but it's written very thick, right? So you'll see in textbooks sometimes the 0 vector is just this really thick, bold guy, right? So that's the 0 vector. Okay. And so if you multiply 0 by any vector, you get the 0 vector. Okay. Those are the quick, boring rules on vectors. All right, guys, I hope that vector review helped and made some sense. There are a lot of practice problems that you should go through if you're not familiar with vectors. A lot of things that you're going to see in physics are going to be described with vectors because a lot of things in the real world have a direction and a magnitude. In mathematics, if you study linear algebra, you're going to see that we give vectors get very abstract, right? I like the physics. I like to start learning vectors in physics because you can have a physical intuition for why we use them, and it seems to make sense. But it turns out that you can use vectors for a lot of things, right? Including like lists of words or ideas. And this is really important. You might think it's silly, but it's the basis for machine learning, is that we take sentences and you can make a vector out of a sentence, and you can talk about the statistical relationship between different words and all this stuff. So that was a really bad and very general description, but it is true that you need vectors for that. So we're not going to go into the linear algebra in this course, but we do need to be set with our vectors. And from here on out, I will assume that you're okay with the basics of the vectors. Again, the one thing we didn't cover today is multiplying vectors. And so we will get to that in due time in the course. You get what I'm saying? All right. The next lesson is a review on calculus. I will see you there for a little bit of review on derivatives and integrals and what they mean in the world of physics. See you then.